Generally, once it comes to learning kind of how to use machine learning, there are roughly 4 stages on how you can adopt it. So the first level is you already know how to solve the problems manually, kind of with paper and pencil or whatever, and then you can I'll answer after the end of this lecture. So, then once you use the large language models, they basically help you to write the code to solve the problem that you already know how to solve. This is actually something where LLMs are absolutely great. And first of all, if you can explain what you want to do, then typically they can do that. And secondly, once they do it, you are able to figure out whether the answer is correct, which is also very important. So the second level of the adoption of machine learning in physical community is when the machine learning comes up with a new kind of concepts or ideas, and then we learn how to adapt these concepts in physics. So the examples of this would be variational autoencoders, so everything related to the latent representations, disentanglement of representations, and so on. It does not have a physical analog. It's something that was created in the machine learning community, and then we learned how to use this type of concepts in physics. So the third level, if you're curious, is there is a principle that there is no computation without representation. So once we deal with the fields or mechanics or whatever, we know we can build the relationship between our real world object and the idealized abstraction. We can go forward and backward between them. For example, if I want to understand how to describe the motion of the celestial object, I really don't care what color are they and what shape are they. All I need to know is their mass and velocity, right? And forces acting between them. So in order to understand the mechanics, we need to know masses, velocities, and forces, but we really don't care about other aspects of the system like shape or color. If we want to understand the internal rotation, we also need to know the shape, but the only thing that we need to know about the shape is the tensor of inertia, and all other characteristics don't matter. So basically what happens is that if we think about the system in terms of descriptions, we can kind of take everything that we can use to describe the world, and in order to build the mechanical models, we need only a small isolated subset of that. So that's why mechanics is a very successful science, and that's why mechanics, for example, is not changed by quantum mechanics at all. It's kind of science in itself. The same type of thing applies for the continuous fields. So we have continuous fields like temperature, whatever, pressure, what's not. We have the partial differential equations that also allows us to describe the part of the world. It turns out that it's not always the case. So in many cases, we don't know what are the minimal descriptors that are required to kind of describe the world and make a self-consistent system of equations describing. So anyway, the idea is that if we want to analyze something by machine learning, we need to take a real-world object and find a way to represent it as the computational abstraction, and that's actually a very big challenge by itself. So in fact, for most people who use machine learning in domain areas, this problem of featureization of description is the primary problem, because once you learn how to do it, then you can already solve that's 90% of solution, and now it's more like 95. And the final problem is the question of why we are doing things. It's called the question of the rewards and the policies. And that's something that we are going to talk tomorrow, and especially pretty much all day on Friday. So anyway, let's go back to the variational autoencoders. So what is autoencoder? It's actually a very, very simple network. Okay, let me turn on the pointer. So imagine that you start with the data. So your data can be images, it can be spectra, it doesn't matter. That's what you do is you start to set this data through the set of convolutional or just multi-layer perceptron type of layers until you reduce the data to the small number of the latent variables. So Elizabeth have given the tutorial about the normal neural networks, and you might remember that if you stop here and on top of this latent representation, you put the classification head, for example, softmax, or you put a regression head, then you will get a kind of classical regressor or classifier networks. But what the autoencoder does is that it takes this latent vector and it goes through the set of the deconvolution operations until you go back to the dimension of the original data set. So the way that you train it, it gives you the data. You start with the data, you get as output something that has the same dimensionality, and then your loss function is basically the reconstruction loss, so the difference between the data that goes in and the reconstruction that goes out. So this is the example of how it will work. So for example, if I make a very simple autoencoder and train it using the MNIST data set, this is how my inputs look like, and this is how my reconstructions look like. So in this case, my latent space was only two-dimensional. So you can clearly see that I was able to reconstruct the objects, but not too well, right? So for example, this 7 has this horizontal line, and this one clearly does not have a horizontal line. So the general shape is somehow preserved, but small details are clearly lost. With being said, it sounds like the autoencoder is a very, very stupid network. Basically, what it does, it learns to reconstruct the data from itself while passing it through this very narrow needle eye of the latent vector. So the interesting thing is that if you look at the publication of Jeff Hinton, who recently got Nobel Prize in physics for machine learning, you can see that autoencoders is one of the most cited paper that has what was like last year. It was I don't know, where is it? 2006. Yeah, this one. So it got something like 25,000 citations. So the question is why the autoencoders are important. So before we go to this, let me introduce several concepts that appear in the context of autoencoders, and that will kind of explain some of it. So first of all, once we deal with the autoencoders, we always deal with the original data, reconstructed data, and the intermediate, this latent vector. So if we take the MNIST data set, then each digit in MNIST data set is 28 by 28 pixels. So what the autoencoder will do, it will compress it to the latent vector. We can choose the latent space to have any dimensionality, but for certain reasons, it is sometimes convenient to use the two-dimensional latent vector, because then we can plot it as the first latent component, second latent component. So in this case, each 28 by 28 pixel image becomes the point in the latent space, because it was 684 dimensional and then it becomes two-dimensional. So one thing that you will, so this is a so-called latent distribution. If you take your old data and encode it and then plot it in the latent space, then what you get is the called latent distribution. Notice one very interesting thing, that if you look at this part of the latent space, you see zeros. If you look at this part of latent space, you see ones. In this part, you see sevens, and then everything else is sitting here. So it's clear that different digits occupy different part of the latent space. Then you can do another thing. So you can say that, look, if I take 0, I compress it, it goes to this part of the latent space, and then I can decode it from the latent space, and then I will presumably get another 0. But I can decode from the part of the latent space where there is nothing. And many of you have heard the word of generative AI, right? The AI that creates new examples of data. So variational autoencoder is the generative AI, very simple AI, but nonetheless generative, because you can choose this point in the latent space where there is no real instance of data. You can decode from this region of the latent space, and you get a new example of 0. So this is what you're going to get. So if you create a if you create a grid of points in the latent space and you decode from this grid, you will get what is called latent representation. So why is latent representation cool? So look, so in this part of the latent space, we have zeros, here we have ones. So if we look at the latent representation, we can see that here all the points are zeros, here all the points are ones, here are all sevens, here there are some points in Klingon, because these points are between 0 and 1s, and there is no way to interpolate between them. But if you look at this image carefully, you also start to notice a very, very interesting behavior. So look at these ones. So one thing that you will notice is that they are clearly not random, right? So if you go from this direction to this direction, you can see how these ones become tilted, and this tilt changes once you move in this direction in the latent space. If you look at these zeros and you go from here to here, you can see that you move through the latent space and your zeros kind of become more narrow and tilted at the same time. So this is, I'll show you more examples of this, but this is what is called the disentanglement of representations. So there is no analog to the disentanglement of representation in the classical physics, at least that I know of. There is no rigorous definition of what it is. It's like one of those things, I know it when I see it. But it's very easy to recognize it because it basically looks like that if your data has some factors of variability, so factor of variability in this type of data set is difference between digits, right? 1s and 7s are different, at least until I look at my doctor's receipts, because when the doctors write, it's very difficult to establish the factors of variability. So another factor of variability is the handwriting, right? Some people write in blocky letters, some of them like tilted, whatever. So what the variational autoencoder does and what the latent representation allows us to get is to disentangle these factors of variability, meaning that they become aligned with the latent variables. This is not a perfect alignment. It's not going to be one-to-one. In fact, if you rotate your latent space, nothing is going to change. It's not even necessarily global, right? Because if I move along one axis, like this direction, zeros become these weird features like 8s, and then it becomes 1. But locally, it is very well defined. Please. Do you have a question? Sure. Yep.
Yeah, question. Question is that the data is not but it sounds like in the other part of the network, it doesn't even depend.
Latent space can be any dimensional, so you can choose it to be 1-dimensional, 2-dimensional, 10-dimensional, or 100-dimensional.
But this specific example,
this example 2-dimensional.
How many people have changed the architecture of the network, but keep the latent dimension 3-dimensional. Still didn't order.
Yes, so the architecture of the network can be anything. It can be MLP, it can be DCNN, it can be graph network, kind of choose your poison. The behavior, of course, would be slightly different, but the key part is that what matters is the latent space. So what can you use the autoencoders for? So interestingly, autoencoders are very good in problems such as data reconstruction. So for example, one thing that you can do is you can train the network where the input is the grayscale image and the output is the color image. You create a large training data set. So it's obviously very easy to make a grayscale image from the color image. You train the network using these pairs, and then you take a grayscale image that the network have never seen, send it to the autoencoder, and then it will decode the color image out of it. So that actually works remarkably interestingly. So this is the example of the test image. So look, this is the ship in the green sea. So this is the decoded image. You still get a ship, but now it's in the blue sea. So why is it happening? It happens because most of the examples on which the network has been trained shows the ships in the blue sea, and green sea is anomaly, and therefore it tries to reconstruct the blue sea. So why is it something that we should be careful about? Imagine that we use the autoencoders for denoising the data. So if we train our encoders on the data that has peak in a specific location, that every noise spike in our test data will show up at this peak. Vice versa, if our training data has 0 in the specific region, then we would not be able to do anything. So the thing is that people are very gung-ho about using this type of algorithm for denoising. It's not a bad idea, but always go to the original data and use the classical hypothesis testing, because autoencoders, I mean, we all know that LLMs can confabulate, right? So autoencoders can also confabulate, and that's something that we need to know and respect. So the same type of things happen if we try to solve the kind of more classical denoising. So if I can use the autoencoder to train it on noisy data to produce the data without noise. Then I can apply it to the test data sets, and the way that it reconstructs is amazing. So this is my noisy inputs, and this is my reconstruction. So the reconstructions look almost like a ground truth. And some of these are very difficult even for human to detect. So it's difficult to see that this is one if I don't have access to this one. But a very interesting example is that train the denoising autoencoders on the digits from 0 to 5 and try to apply it to the digits from 6 to 9, and you will be surprised. So the performance for those that it has not been trained on will drop appreciably. But it will not drop to 0 because, let's say, 8 and 5 look remarkably similar, at least as far as autoencoder is concerned. So if your 5 was in the training data set, that 8 could also be kind of sort of denoised to some extent. Now, the important thing that if it's not enough with autoencoders, there are also variational autoencoders. There is a difference in how the latent space is sampled. So the autoencoder is the rigid architecture, you just decode latent space. Variational autoencoder probabilistically samples the latent space. From the point of view of the how they're used, the difference is relatively small, but kind of the difference is in the how the latent layer is sampled. So the variational autoencoder give rise to the same object. So we have the latent manifold and latent representation. We have the latent distribution for the data. So this is kind of the example of how the autoencoder is trained. And this also allows us to illustrate this concept of the disentanglement. So imagine that this is autoencoder latent representation. So we have 9s, 1s, 7s, what's not. So you can see that parts of the latent space are not physical, right? So these are not the normal digits. So this is how it looks like when we try to do the autoencoder if we just choose it to train it on one digit. So in this case, the only factor variability is the handwriting style. And you can see that here there are nice 7s, and here this is not physical objects. So this is what happens if we train the variational autoencoder. So if we train it on the full NIS data set, you can see that all latent space is basically meaningful. So there are 1s here, 0s here, 6s here, 7s here, and so on. If we train the whole VAE only on the digit 7, you can see kind of the disentanglement of representations in a fairly beautiful way. So in any direction, if you move across the latent, in some direction latent space, you see that the character of the writing changes systematically. Very, very clear. And obviously, I show you the example for images, but obviously you can do this type of things for spectra or for images from microscope and so on and so forth. So this is another example when we do it for number 8, digit 8. And there are some interesting things that we can do with this type of latent representations. For example, imagine that one of these directions can be identified with the width of the handwriting. So the way that you do that is that you take your autoencoder. For each digit, you need to have a label, which means the width of the handwriting. If you have that, then you build the relationship between the direction and the latent space and your label. You basically say that this direction in latent space corresponds to width, and this direction in the latent space corresponds to the tilt. If you do that, you can take your digit, written by one person, for example, Gerd writes something, we put it in the latent space, we shift it along the direction corresponding to the width, and then we decode it, and then we have the different person handwriting. So as you can imagine, this type of things are super useful for things like fake images and so on and so forth. So if you've seen all these filters in the TikTok or Facebook or whatever, when you take your picture and show you how you will look without glasses or with a bird or whatever, this is roughly how it was done, let's say 4 years ago. So now we can do it much better for the diffusion models, but 4 years ago, we will do it with the autoencoder type of architectures. So another thing that we can do with the autoencoders, so I showed you an example of training the autoencoder using the whole MNIST data set or only sevens. In fact, there is a way to do it more elegantly when we build what is called a conditional autoencoder. So in this case, we have the data instances and we have classes. We assume that classes are known, and the class becomes a part of our latent vector, and then we decode from latent vector and the class at the same time. So if we do that, we get a very interesting thing that each of our known classes gets its own latent space, and what you can see is that this disentanglement of representation looks the same in each latent space. So notice that 6, 7s, 8s, and 9s, they're all kind of vertical and chubby here. They're all narrow and tilted to the left here, and they're all narrow and tilted to the right here. So basically, when we know classes and we know that the factors of variation are the same between the classes because handwriting is the same for each person, the conditional autoencoder is the way to separate the classes from the variation factors of variation specific to each person. So there are many other things that we can do with autoencoders. So one of the very important things that appears in the context of the image analysis and microscopy is the consideration of the invariance. So what I mean by that is that imagine that you look at the object in your microscope, right, and you see something. So generally, in many cases, we don't know what is the right orientation of the object under the microscope. It can be oriented like this and can be oriented like this. We just don't know. So there is a way to take the autoencoder and make this invariance as the part of the decoding process. So it's a kind of separate variable. We can do the same type of things for the translation. So that also is very important because when we see an object in the microscope, we don't have the fixed reference point. Like imagine you see multiple nanoparticles. So one way to analyze them is to reference each nanoparticle to the center, but that we already have to find nanoparticle and find the center of gravity. There's no guarantee that we do it correctly. If we take a random patch, we don't expect any alignment between the nanoparticle and the center of the patch, so it can be anywhere within the image, which means that this becomes a factor of variability that will be much stronger than anything else. So it turns out that autoencoders allow us to introduce this function of variability as something as the independent latent variable that we can actually separate from the normal latent variables. So let me show you an example of how it works, and we have a very detailed tutorials where this type of methods are introduced. So imagine that so MNIST dataset has 10 objects, right? It's a little bit more complicated. So let's say that we take a data set of the cards. So this is kind of diamonds, clubs, spikes, hearts. And let's say that we introduce the 4 data sets which vary in terms of rotational disorder and the shear disorder. So they're rotated randomly and they're also kind of sheared. So imagine that this is our first data set when we have low rotation and low shear. So this is the example of the data. So this is just this object chosen randomly. This is the latent representation. So in latent representation, you can already see that hearts are sitting here, spikes are sitting here, clubs are sitting here, and diamonds are sitting here. So this is your disentanglement. Second thing that you will notice is that the reconstructed objects and the original object look very similar. They're both sharp. It tells you that reconstruction loss is sufficiently small. And now what you see here is magic. So what we do is we take our data set, we encode it to the latent variables. So each image becomes a point in the two-dimensional latent space. Then we plot this latent distribution in the latent space. And as the color, we use the ground truth label. So here the ground truth label is the suit. So you can see that we have suits are very well separated. So if you go in this direction corresponds to the factor of variability between 4 different types of cards. So here you can see that the angles of rotation change in this direction, so they're perpendicular to the suit. And you can see that they change in the same sense. So the low angles are here, high angles are here, but then this one becomes a low angle again. So somehow angle of rotation become a smoothly changing latent variable. It's not linear, it's kind of more like parabola, but still it happened. And then what you see very cool is that the shear, at the first glance, it looks like it's random, right? But if you look at this one, you can see that here shear tried to locally disentangle and form this kind of rainbow. That means that locally it tries to separate in the direction perpendicular to the angle. So you see that this factor variation and this factor variation and this factor variation are orthogonal to each other, right? So this is a super powerful method. So for people who want to do physics by simplifying system, this is just absolutely amazing. So let me show you another example. So here we take a data set where shear disorder is stronger. So look what happens in this case. So now we still have a separation between the different suits. You still can see that the factor variation due to shear and the angle is orthogonal. So the gradients in this image and gradients in this image are locally orthogonal. But it's very clear that we have 3 factors of variation: the suit, the angle, and the shear. But we try to squeeze it in the two-dimensional space, and we cannot do it very well. So they kind of start to conflict with each other. So if we take the high rotation and low shear, then we get something like this. So when you see pictures like this, you know there is a concept from astrophysics called spaghettification. So if you fall on the black hole, you are going to die because somehow you got extended infinitely. So that's kind of how it looks like in this case. But again, we see the disentanglement between the relevant variables. Then if we have the high rotational and high shear disorder, you can see that, first of all, our reconstruction loss becomes large. So you see that reconstructions are not perfect anymore. And then our latent distributions start to look like a nightmare. So the orthogonality and disentanglement is still in place, but it's very local. So what's the problem with local? The problem with local that we can see that it's happening if we have the ground truth labels. But if we did not have the ground truth labels, this would be kind of useless for us. Comparatively, if the data is like this, we can kind of guess the ground truth label because the distribution in the latent space is very well behaved. Now, if we go to the rotational autoencoder, so basically what the rotational autoencoder does, it takes our data and it tries to separate the latent space, latent variables, and rotation angle as a separate latent variable. So technically, we have 3 latent variables, 2 classical and 1 rotation. But notice what happens in this case. So if we take our low rotation, low shear, we basically have 4 points, and our shear is kind of changing in this direction. Our suit changing in this direction. And what's interesting is to compare the ground truth rotation angle and the reconstruction of the autoencoder. So notice that this changes from -0.2 to 0.2. This changes from -0.5 to -0.1. So there is actually an offset. There is no way for the autoencoder to know that the correct orientation for diamond is like this, but not like this. But the trend is the same. So we truly were able to disentangle it. So if we take low rotation, large shear, things look like this. So in this case, the disentanglement in one direction is the suit, in another direction is shear, and angle is a separate variable. And even in the cases when the disorder is relatively large, the results are pretty good. Now, what's interesting about this data set, it shows another interesting property of the autoencoders is that there is no guarantee that the way that the autoencoder trains, it will give you the ground truth behavior. So notice what happens in this case. So if, as far as I remember, my label 2 was the diamond. So notice that I have two groups of in latent space corresponding to diamonds. And the difference in this here took place is clear that there is a jump in angle. So what I think has happened is that autoencoder decided that diamond in this orientation and diamond in this orientation are two different diamonds. And there was no way for it to know that it should be a single one. So point is that there is no magic. Machine learning is generally not a silver bullet. So once you run this type of analysis, they allow to do some things, but not other things. And they have a very kind of specific type of artifacts that you can understand using the model systems. And then you can keep an eye open for this type of artifacts in the real world applications. But even for the high rotation and high shear, it actually works remarkably well. So you get something that's well behaved. Compare this latent representations to this latent representation. This is chaotic, and this one is complex but reasonably well organized. Now, as I mentioned, this is how the autoencoders work, and this is what happens when you make them rotationally invariant. So another problem that we often deal with if we have the multiple classes. So if the classes are known, we will use the conditional autoencoder. If there are a factor of variability, but they're continuous, then we have continuous autoencoders. Very interesting problem is when we know some classes. So example is very straightforward. Imagine that you have a microscope and you have collection of samples. And the samples would be pollen or leaves or whatever, sort of choose your favorite object. So you know that they come from different classes, right? And these classes have some internal difference, like the leaves coming from the same type of tree would be different. Pollen coming from the same type of tree would be different, but then somehow human can look at leaf from this tree and recognize it from the leaf of this tree, right? So at the same time, let's say that you have a textbook which shows you the schematics of the trees, of the leaves from this particular tree. So something like a classical botanical textbook from the 19th century. So humans somehow are very good at looking at the example in the textbook and finding similar objects under the microscope, even though technically they look totally different, right? So somehow we managed to capture the salient elements of the object and recognize in the real world setting. So another example can be, for example, I've never seen, even if I saw something like armadillos only in the book or drawn manually, somehow I would be able to recognize a real armadillo, right? So the real armadillo as I see it would be very different from the kind of simplistic drawing, but somehow we can do that. So that's exactly the type of problem that the semi-supervised variational autoencoders are solving. You train them given the large amount of data and small amount of label data. So imagine that you manually identify 10 objects out of 1,000, and then the autoencoder will disentangle the representation of the data, but it also will assign the labels to the 990 object that you didn't label itself. And this, by the way, is a very, very interesting thing about machine learning, because if we deal with the low-dimensional systems, like we solve regression problem, we know that there is a lot of value in having XY pairs, but almost no value in having additional X values, right? It's just meaningless. When we deal with the high-dimensional objects, there is a tremendous value in having a small number of XY pairs and large number of pure X values, because there is a cool thing called the manifold hypothesis, meaning that high-dimensional objects are not random in high-dimensional space, they occupy some manifold. And having a large amount of unlabeled data helps you to find this manifold, and then small amount of labeled data allows you to do the identification. So this is what semi-supervised VAE are doing. And then if you don't have examples, but you just know the number of classes, this is can be done by so-called joint autoencoders. So as an example, this is how it will look like if we have the MNIST data set. So this is the conditional autoencoder if we have no rotation or rotational invariant. So this is a MNIST data set when we rotated it in many different directions. You can see that in this case, it's kind of interesting that the latent space is occupied by ones at different rotations, but in the center, this is unphysical. Same thing happens for 8s. So 8 has different orientations, but nothing in the center because we simply don't have examples of 8s with the 0 rotation, and we try to impose the symmetry that's not a part of the data set. So once we have the rotational invariant autoencoder, we just found the rotation angles. Oops. So this is the example of how the joint VAE does. So the problem with the joint VAE is always that we either don't know number of classes, or we do know the number of classes, but there is absolutely no guarantee that the way that joint VAE will classify our object would be corresponding to the ground truth. For example, if I take the MNIST data set and I try to separate it in 6 classes, then you can see that zeros become one class, ones become another class, 60s is kind of sort of worked, but 5s, 8s are mixed, and 3s and 2s are mixed. If I try to separate it in 18 classes, you can see that there are more than one class correspond to 0. There are a class which is somewhere between 7 and 1s. There are several classes corresponding to 6s. Basically, the reason why it happens is simply because the difference between how some people write zeros is larger than the difference between how some people write zeros and some people write ones. So just as simple as that. And even if I take the right number of classes, their mixing is not perfect. So it can tell us something, but it's not guaranteed to give us ground truth answer. There is no way to rigorously establish this behavior, but what sometimes happens, so remember, I told you that one of the indicators, it's not the proof, but an indicator of analysis being correct is that it is robust. So one of the ways to check the robustness is to transform the data a little bit and see if the results of the analysis are the same. But we often do it as a part of the augmentation of the data before training. So another way to establish the robustness of the data is to take the collection of the network. So rather than training one network, take 100 similar networks, initialize them differently and train them separately, and then compare the outputs. So calculate the average of the output and the dispersion. If the dispersion is small, that means that the training is robust. If it is large, then it's not robust. And in fact, this type of ensemble approach works remarkably well whenever we need to get some estimation of the prediction and uncertainty. For example, for decision making, that's one of the ways how we can do that. So what else can we do? So the question is, how can we apply this type of methods for imaging and spectroscopy? So for spectroscopy, it's very easy to start because we can just treat the spectrum as the instance of the data, and just we start with our 3-dimensional data set, we dump it in the autoencoder, autoencoder gives us an output, the latent variables. So then for each location XY from which we took the spectrum, we plot the latent variable. So that's how we get the map. Notice that if we do this type of things with it's kind of reminiscent of what we do with the clustering, except that for clustering, we plot a discrete cluster label, and here we plot a continuous latent variable. There is a similarity with the linear decomposition, but for linear decompositions, we get the loading maps and the components. And for variational autoencoders, we get only latent variables. So where are the components? The components are weights of the autoencoder. They're hidden inside the neural network. So we have only latent variables. So the question becomes, how do we analyze the imaging data? So this is kind of complicated because analyzing the imaging data requires building the descriptors. Building the descriptor means that we need to postulate some form of the physical bias in the data. So notice that we all think that kind of bias have multiple meaning, right? In the social setting, bias is not good. In case of machine learning, bias is inevitable. There is no way in machine learning world to avoid biases. There is always a bias. The only thing that we can do is we kind of postulate what the bias is. That's what best we can do. We cannot compare whether they are good or bad. So how can we do this? So one way to make our descriptors is to use the sliding window transform. So this is the case where we essentially, our bias is continuous translational symmetry. If our system indeed has continuous translational symmetry, that's the right approach. If not, then it will be bad. So another way we can describe images is to find all the features, for example, atoms, and analyze it as a collection of atoms. So I'll show you examples of how that works. Third way is a kind of combination. We can find all the atoms, but then we can form the descriptor as a patches, centers of these atoms. So this actually ends up being the most useful one because on the one hand, we respect the fact that atoms do exist, but at the same time, we also analyze the data that is not a part, which is not included into the atomic position. So let me show you a few examples. So this is an image of the nickel oxide integrals inside the LSMO. So if we want to analyze it, first thing we do is we find all the atoms. So this is the example. So we found all the unit cells in the perovskite. We found all the, or most of the unit cell in the rock salt. We form the descriptors. So the descriptors are image patches. Then what we do is we dump all the descriptors in the autoencoder. So each image patch becomes either two latent variables or two latent variables, rotation angle and translation. So it depends on what type of autoencoder we have chosen. And lo and behold, we start to see something interesting. So for example, these are the standard latent variables. So you can clearly see that the two phases are very well separated here. But you also start to see some other things. So for example, notice that this part of the image has a slightly brighter contrast, right? Which you will not be able to notice in the raw image. You also will notice that one of the latent variables shows some interesting features which are clearly not a part of the atomic contrast. So notice that this latent variable is the same inside of nickel oxide and inside of LSMO. But there is something changing between these nanoparticles in this region. So the most obvious explanation that somehow we detected the strain field, it needs to be proven, but the fact that this approach allowed us to visualize factors of variation, and some of these factors of variations are non-trivial, is just right in front of you. So we can also analyze the latent representation. So in this case, it basically corresponds to change from A site to B site type of atom. We can try to analyze the angles if we want. And again, we start to see that in some form of, in some latent variables, we start to see the noise effects, which are very clearly separated. Like for whatever reason, X offset start to accumulate this type of lines corresponding to the scanning instabilities. So we can obviously keep exploring this tangent. For example, if you create your latent distribution, you can further cluster it. So you can cluster the original patches, or you can cluster the latent vectors for the patches. Results would be very different. You can interpret what it is because you can always look at how this looks like. So this is A site, B site, and the rock salt phase. That's the reason why we introduced the joint autoencoder, so we can classify by itself rather than trying to do it in the latent space. But then, as I said, the interesting thing is that sometimes we can get much more subtle effects. So for example, if I try to apply this type of analysis to the single crystal, where there is no second phase, there's no imperfections, you can see that one of my latent variables has the feature on the left. So where do you think it comes from?
Yeah.
Exactly. This is a flyback delay. So as simple as that. So the small scan distortion that you cannot see by eye is found by the autoencoder remarkably well. So this was an example of autoencoder with finding atoms. In principle, one of the thoughts was in developing the translation invariant autoencoder was that we should be able to apply it to periodic patterns without finding the characteristic features, and then the translation would be separated as a separate latent variable. So if we have the intrinsic periodicity and the sampling square, then it's not aligned in any way, so there is some random translation vector, so maybe we can separate it. This kind of sort of works, but it's very difficult to make it work robust. So it's kind of an interesting, for those of you who are interested in ML, that can be an interesting project going forward, because if you manage to make it work using the LLMs, that would be the tool that can be kind of useful. So imagine if I try to take the image of Bithyne ferrite or the same nickel oxide LSMO and try to analyze it using the autoencoders, but when my descriptors are simply a sampling grid. So if I use the simple VAE, the first image will look like this. So this is the analysis. Second image will look like this. So you can see the second phases, but the image looks horrible. So what are we looking at? So what's the origin of this behavior? So first of all, where do these patterns come from? So this is a simple Moiré pattern that our image have one atomic periodicity, our sampling grid has a different periodicity. When we superimpose two objects with a different periodicities, we got the beating pattern, and this is how this beating pattern look like. So the second thing that you will notice is that the latent distributions in this case are fairly complicated, right? So this one is completely complicated, multiple kind of one-dimensional manifolds. This one is slightly simpler, but still kind of complicated. Remember what I told you, that one of the big lessons in the ML analysis of the data is that sometimes the way to explore the data is to take the tool with the right physical bias, and we know that the bias is right when the analysis results are simple. So in this case, the analysis result is complicated. It's not clear what it is. So if we spend some amount of time and effort in order to convince the shift invariant autoencoder to converge, this is what simple means. So this is the example of the ferroelectric domains. So our original image looked like this. So this is substrate. Here there are ferroelectric domains that you cannot see very well. So if the autoencoder confirms the converge, then you can clearly distinguish the substrate one domain orientation and second domain orientation. And your latent distribution, so the blue dots are each patch, the superimposed the kernel density estimate, so it shows you where the data is localized. You can see that there is one peak, another peak, third peak. So this corresponds to one domain orientation, this corresponds to another domain orientation, this corresponds to substrate. So we found a simple representation. Compare it to the representation when we did not find a simple way to represent it. So here it's even better. You can see only two peaks. So one peak corresponds to one phase, another peak corresponds to the second phase, and even your latent distribution, so latent image shows the phase region, and this one is kind of uniform. So this latent variable basically does not change. The important thing is that autoencoders sometimes collapse, in which case the Z changes very little, but in this case the range is healthy, so it's not collapsing. We truly found the right way to represent the data. So logic is exactly the same as you will use for finding the coordinates to make your data straight, except that you do it with much more complex data sets. So what else can we do? So we can use the same type of approach for the chemically disordered systems. So this is the example of the graphene in the microscope. So this is graphene, this is holes, these are silicon atoms, this is the contamination. So we can use neural network to find all the carbon atoms. It's interesting. Oops. So this is the example of how the autoencoder trains. So this is the dynamic of graphene, and this is dynamic of the latent space with the training. So you can instantly see that the latent variable tells us something about the structure. So if the graphene is ideal, then you have a high latent variable, it's red, and close to the defects, we have the latent variable is lower, so it's either green or blue. And here we can do some very interesting things when we try to tune out encoder to maximize the decoding power so that the reconstruction loss is smallest. In this case, if we look at our latent space, you can see that the elements of the latent space look like a textbook examples of the carbon configuration. So here they are almost ideal, 3 carbon rings. Here you can see the 7-member ring. Here you can see 6 and 5-member ring side by side. So it's actually pretty cool. And it is especially cool if you try to figure out what it means, because one of the biggest problems in machine learning is that it's very difficult for us as humans to judge whether the machine learning result is trivial or not trivial. So in some sense, a few years ago, I kind of come up after dealing with too many reviews from journals, I came up with the joke that we cannot discover new physics by machine learning, because if we understand what goes on, then it's not new, and if we don't, then it's not physics. So now the situation is slightly better because there is a small gap between what we know and understand, what we know and what we can understand. And sometimes machine learning can give us an answer that we can understand, but we did not expect before. But that's a fairly recent development. So one good way to recognize the new physics is kind of add a little bit of the schizophrenia to your mindset. So divide your brain between 2 parts. One part is what you know, and another part what machine learning algorithm knows. So the part that you know, that you use in order to interpret the machine learning output, this is the human interpretability. The part that machine learning knows is the inferential bias that you put in the system. So for example, if we look through this process of going from raw observation to the DCNN segmentation, we basically postulated that atom exists, discrete, and have a known shape. That's what went into the creating the training set for the DCNN. Once we take the DCNN data and try to find these latent objects, the only assumption we are making is that the structures exist and the structures are parsimonious. There are a small number of variants. And then once our autoencoder creates this type of structures, it basically means that it took large volumes of imaging data from microscope, and it was able to discover the existence of the molecules or kind of these graphene segments out of this data. The fact that we recognize this as coming from the organic chemistry textbook is a human variability, because we read the textbook and the autoencoder did not. But anyway, this is something that we can do, and we can always kind of explore how these objects are distributed in the latent space and so on and so forth. Now, the last thing that I want to briefly show is the issue of constructing the structure-property relationship. So for the time being, I've showed you that we can take the data, compress it, expand it, and then derive a lot of meaning out of the latent representation. In the beginning, I also have shown that we can use this autoencoder for denoising or reconstruction of the images. But it turns out that very often the problem that we encounter in microscopy is the problem of reconstruction of structure-property relationship. Like I have the image patch, I want to get an idea of how would the yield spectrum from this region look like. It's usually straightforward, so I can collect a lot of pairs between the structures and spectra. So, and what we can use autoencoders for is to create the network where we have the pairs of image patches and spectra. We train it using the images as the input, but then the decoder will try to build the spectrum. So this is kind of the example of how this will look like for plasmonic particles. So this is the image. The blue is the ground truth Hill spectrum, and the orange is the prediction. So as you can see, it's actually not too bad. So there is very close agreement between the prediction and the spectrum. We can try to do inverse problem. We can train the autoencoders using the spectrum as an input and the image as the output. This, of course, doesn't work very well because images are much more complex and they also have the possible orientations. But even this kind of works. For example, what? Okay. Is it 50? Oh, okay. Yeah, I thought it's an hour. Okay, anyway, so this kind of works. It captures the relevant elements, but not works in full. And then it turns out that the better way of doing it is to build what is called dual autoencoder. So imagine that we have a pairs of images and spectra. So in this case, this is SEM image, and this is the far field spectrum. So what we can do is we can create the autoencoder architecture where as the input we have pairs of images and spectra, as an output we have pairs of images and spectra, we have one encoding head, another encoding head, but they are forced to encode the image spectra to the common point in the latent space. And then they decode from the common point into the reconstructions. So if we train this type of autoencoder architecture, then for the unknown system, we can take the image, encode it in the latent space, and then decode the spectrum. So then we kind of start to solve the problem of the reconstruction of structure property relationships. And this is the example how it works. So this is the examples of the spectral data set. This is the ground truth, and this is the prediction. So notice it works remarkably well. So 3 particles become 3 particles, 4 particles become 4, but with a different orientation. Kind of 5 become 4, dimer become dimer. So it actually works remarkably well. The confusion matrix is very, very impressive. Now, the part which is super impressive in this case is that very often with machine learning, we have a problem, how much data do we need? So the dimensionality of this data is very large. If I'm not mistaken, it was like 1,600 dimensions. The number of instances of data was something like 300 because each of this point was, you need to manually measure it. So the dimensionality of data is much larger than the number of instances. The number of examples corresponding to this type of shape, it was like literally 5. And despite the fact, it actually still worked and produced the results. So if you want to know more about it, we have a big review paper that came out about 2 years ago, which talks about the autoencoders with the very detailed tutorial on this. And there is a journal with the code that Microscopy Society tried to start, which basically shows the work-through examples of the VAEs, rotation invariant VAEs, and so on. So if you go to this website, you would be able to basically run the codes and explore the same examples as I've shown. So any questions? Please.
When you were going over the spectra and the images, what mechanism did you use to make sure that the spectra and the images map to the same point?
We just acquired them this way.
You what?
We just acquired it this way. We basically simultaneously acquired the image patches and spectrum, so they're perfectly registered. Practically, if you want to do it, you can either take the EELS data set and generate the images by projecting on XY plane, or you can take a high resolution normal image, EELS data plane, do the nonlinear registration, but then you basically build the core-registered image patches and spectra corresponding to the center of the patches.
Perhaps I misunderstood, but you didn't mean that you are also having the spectra and the images mapping to the same point in latent space?
In the dual VAE, we do.
Yes, and what was the mechanism you used for that?
We just force the latent point to do the same.
As in, like, you put a distance metric on them so that they had to match, or?
So technically, there are several ways of doing it. So the example that I've shown was the rigid registration, which just physically force it to be the same latent point. But it's latent point that's trained both by spectrum and image. If they were trained separately, they would kind of be very different, but they're forced to be, it's essentially training on the joint object. There are other ways you can do it. So the more flexible way to connect them is to define the matrix, which is the average distance between the latent manifold for spectrum images, and then you try to align them on average, but not point by point. That one worked, but not as well. So factor variability. So factor variability, what is factor variability? So factor variability is a very good question. So basically it doesn't have a rigid definition. It roughly means what changes from instance to instance of the data. So as a simple example, imagine that I want to analyze the hand gestures, right? So generally, hand is non-linear object, right? So it can have different shapes, but generally the type of the gesture that the hand can adopt is basically limited by how the joints work. So the normal factor variability is, for example, something like this. It's a non-linear factor variability, but it's kind of well-defined. This type of shapes are highly uncommon, so this is not a common factor of variability. For the handwriting, the typical factor of variability is tilt and width. So it doesn't have if we create the ground truth data, then we can make our own factors of variability. Like if I create a data set of images, I can use rotation, shear, or any type of transformation as the known factor of variability.